And we're off. I take it everyone here has had Physics 1. Okay, mechanical forces, laws of motion. Well, now we're going to start talking about non-mechanical forces, field forces, things that do work at a distance, non-contact forces. And we're going to start with electric charge and the electric field. Just so if you want to know what I want to cover today in this class is Chapter 16, Section 1 through Section 6. We get the word electricity from the Greek word electron. Who knows what the Greek word electron means? What did it mean to a Greek? Obviously, to us, it means a fundamental part of an atom. But what did the word electron mean to the Greeks who used it to name electric forces? How many of you have seen Jurassic Park? Electron is the Greek word for amber, for that fossilized tree sap that Sam Neill drilled dino DNA out of and, terrorized Burbank. Long before scientists started working with electricity and magnetism, the other field force that we're going to concentrate on this semester, they were aware of these forces. I mean, they figured out that, some rocks attracted iron. And they called it magnetism, or we do anyway. Then, for centuries, long before any modern day scientists, the philosophers and scientists of old were aware of this force. They knew that if they took rabbit fur and they rubbed a piece of amber with it, that it would develop what they called a charge. And they called that charge an electron or electric charge. How many of you are familiar with the Benjamin Franklin's famous kite experiment? Yeah, okay. Ben Franklin did not invent electricity. Okay, what he did was he did do some experimentation with electric forces. Okay, and what he observed and what others observed was that if you rubbed amber with a fur, a cloth, rabbit fur, whatever, it would develop a charge. And it would repel another piece of amber that was charged in the same way. And that's how they knew that it was charged. It would repel. It would push away another piece of amber charged the same way. They also found they could do the same thing with a glass rod. That they'd charge up a glass rod by rubbing it with fur, and they could charge up, two of them, and they would push against each other. But then, they also found out that if they charged up a piece of amber and they charged up a piece of glass rod, they would not repel, they would in fact attract each other and come together, acting at a distance. Whatever this field force was, it would attract them. And so, it was in fact Benjamin Franklin who arbitrarily said, well, the charge on the glass rod is positive, and the charge on the amber is negative. Those signs are simply algebraic signs. They were the mathematical notation that allowed him to describe the phenomena that he was observing. And he came up with the law, or somebody came up with the law that said like charges repel and unlike charges attract. If Ben Franklin had done it the other way around, then today we would call the protons negative and the electrons positive. But it is truly an arbitrary mathematical artifact. That's it. Physically, I'm not honestly don't think anyone really knows for sure what it actually means in terms of the physical reality of electrons and protons. How many of you are here from an electronics background? Instrumentation, electronics? All of you? Okay, how many of you have studied semiconductor theory? PN, doping, pentavalent, hexavalent? Okay, then you're all familiar with electron flow versus hole flow, right? The flow of the electron flow, the electrical flow of energy through a semiconductor can just as easily be expressed mathematically. It can just as easily be described as the holes moving through the semiconductor as it can the electrons, right? Is there any way to empirically demonstrate one or the other is true and that the other is in fact false? Actually, there is. I can empirically prove to you in what scientists call a thought experiment, I can empirically prove to you that it's the hole flow that actually happens, and that the electron flow is just the hypothetical, fictional. It has to be the hole flow, right? Because the holes are what carry the smoke. And if you ever let the smoke out of any semiconductor, it won't work anymore. Right? Have you ever had one keep working after you let the smoke out? Thus, it is empirically shown that, okay, obviously I'm being facetious, but I am trying to prove a point. It all depends on perspective. And it all depends on it all starts with what you believe to be true. Okay, how many of you have heard the expression, numbers don't lie? How many of you believe that? Well, there's Samuel Clemens, Mark Twain, I think, famously said, I think that was who said it, said there are three kinds of lies. There are white lies, there are damnable lies, and there are statistics. Numbers, in fact, don't lie. Neither do words. Mathematics is just a language. It's a language we use to describe the phenomena that we observe. Okay? And like any language, numbers don't lie, neither do words. Every word has a well-defined meaning. Numbers don't lie, but people do. I'm going to make this point to you. You may have already seen this. If you haven't, follow along. Given that A equals B, for example, 1/2 is equal to 2/4. Two different numbers, but they're equal. A equals B. A squared, then, is equal to A times B. Right? And A squared minus B squared is equal to AB minus B squared. Do the same thing to both sides of the equation, still true. Factor both sides. How do you factor a difference of squares? A plus B times A minus B is equal to, factor out the B, times A minus B. Cancel that on both sides, you end up with A plus B is equal to B. But A is equal to B, so B plus B is equal to B. Therefore, 2B is equal to B, and 2 is then equal to 1 QED. Just mathematically proved that 1 and 2 are equal. Now, who believes that? Who is lying? The numbers or me? And who can tell me where the lie is? I'm going to let y'all stew on this one for a week.
The worst part about all that is we've always been taught in school, like when a professor or a doctor or somebody writes something on a board, fact, gotta believe it.
Yeah. No.
2 equals 1.
I can no, I can be as wrong as anybody. I'm going to let y'all stew on this one for the week. See who can show me what the error is next week. If y'all have it by then, yeah, I'm sure you can, because I'm pretty sure you can ask Google and Google will tell you. Yeah, you know what? I don't want to turn this into a distraction. So if A is equal to B, what is A minus B? At this point, we've written 0 is equal to 0. And at that point, anything times 0 is equal to anything else times 0. Up till here, everything is true. But how did I get from here to here? I divided both sides of the equation by A minus B. And division by 0 is undefined, because you can never know what the result will be. It's in this little bitty nether region right here that you find the lie. Take that to heart. In fact, I'm pretty sure I don't know that I'm going to keep it in there, but I'm pretty sure that there's one question in one of the labs that you're going to get to in this course where it says, blah, 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 blah. Why not? And the answer is because blah, 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 blah is false. You can. And that's actually in one of the labs. I'm not sure that I'm not going to take it out, but remember that and keep an eye out for it in case at some point during the semester you spot it. If you learn nothing else, learn this. You can always find the error. Error can sneak in and it can completely mess you up. Now, in this case, it was pretty obvious that there was an error here. Hopefully, it was intuitively obvious to everyone that, no, this is not true. Now, get back to our actual class. It is credited to Benjamin Franklin that he is the one who assigned the charge symbols to the electrons and protons, although he was actually assigning it to the amber as opposed to the glass. Mathematically, everything would work exactly the same if we swapped them around. And in fact, what you're going to discover is that the E, the fundamental charge of an electron, is defined as a positive charge. So the charge of an electron would actually be written as negative E, and the charge of a proton as plus E, or just E. Because it only makes sense that the charge of a proton, P, should be E. In fact, it makes no more or less sense than using the letter E to symbolize the number 2.718 ... the base of the natural logarithm. So, there is another, I call it a law here, and it has been empirically demonstrated repeatedly, so there's no reason, now at this point it would have to be disproven to no longer be considered a law, and that is that there, in any process, you can neither create nor destroy electric charge. You start off with a finite quantity of negative electric charge and an equal quantity of positive electric charge, and you can separate them, you can isolate them to separate bodies, you can move them around, but you can never create or destroy either of them. So you start off with a body that is electrically neutral. You might set some electrons off of it and cause it to become positively charged, but those electrons go somewhere. They don't just get destroyed. Eventually, if you go higher into physics, you're going to get into high energy physics, and you're going to learn about antiprotons and anti-electrons and find out that, oh yeah, you can, because if you bring a positron in contact with an electron, they're going to annihilate one another. The energy of the mass will be released. But that's way beyond this course. For our purposes, we're still going to consider that electric charge cannot be destroyed or created. Yeah. We're going to talk about, let's talk about the what is this? Is this the Bohr model of an atom? Let's talk about this model of an atom. You start off with a nucleus of protons or positive charges. And electrons orbiting those positive charges. This is how the atom is neutral, because it has the same number of protons as electrons. And so that atom electrically is neutral. The charges balance out, they counteract each other. But not all molecules, and everybody does know the difference between a molecule and an atom, right? Okay, not all molecules, all molecules are neutral in their natural state, but they don't necessarily act that way. Let's talk about a water molecule. You got an oxygen and two hydrogens. The electrons on those hydrogen atoms are very loosely bound. And so they can, in fact, move down and shift over into to the other end, not all the way to the other side, but they'll shift over towards the oxygen atom, leaving the hydrogen atoms kind of positively charged on that side. This creates a dipole moment. We're going to get to that. But it's called, why we call this molecule a polar molecule, because the charge, even though the whole molecule will remain neutral, so if you look at it from a distance, it's going to seem like it's very neutral, but if you get up close, you'll find that there is some charge separation there. It's slightly negative on one side, slightly positive on another side. That is why water is one of the most powerful solvents you're going to find on this planet. But how do we get there with charge shifting? Everybody here has experienced touching a doorknob and shocking your finger, or shuffling your feet on carpet and zapping your friend's ear. We call that static electricity as opposed to kinetic electricity as opposed to flowing electricity. And it happens when electrons are shifted from one body or one object to another. In the case of the amber and the fur, you rub the fur on the amber and electrons are stripped off of the fur and deposited onto the amber. So no charge was created. The fur became more positively charged and the amber becomes more negatively charged. Do the same thing with a glass rod and the opposite happens. The electrons are stripped off of the glass rod and onto the rabbit fur. So the fur becomes negatively charged and the glass rod becomes positively charged. There are two ways of distributing charge in an object. One is by conduction and the other is by induction. Okay, if you want to charge something by conduction, if you take a metal rod that's a good conductor, and you get it charged up with excess of electrons, so it's negatively charged. You bring it over and you touch another piece of metal with it. Some of those electrons are going to flow off of the first piece of metal and deposit onto the second piece of metal. The charge is going to distribute over both bodies equally. And you're going to end up with two negatively charged pieces of metal. Neither will be as strongly charged as the original was to begin with, but they're both still going to be charged negatively. That's by conduction. You can also charge by induction. You take a metal rod, and it has however many atoms of iron are in that rod, it has that many atoms, and so it's got all those electrons. And because it's a conductor, they're very loosely bound. They're basically free to move around from atom to atom as as forces act. So if you take another strongly charged, or weakly charged for that matter, take another metal rod or some other object that is negatively charged, and you bring it close to this metal rod, it's going to push these electrons, all these excess electrons in this rod are going to exert a force on the free electrons here, and the electrons are going to start separating. So at a distance, this rod is still neutral. When you get up close, and you're going to find that it is much more positive on this end and much more negative on this end. Take away the charged rod, these electrons immediately redistribute and it becomes locally neutral again. What if you take this rod and you ground it? Everybody recognizes the symbol for earth ground, right? Okay. You ground it to earth. Earth is a giant reservoir. It's like a big source or sink of electrons. You can source electrons from it. You can sink electrons to it. That's why you only needed one wire for a telegraph. You ground this thing and bring this rod up close. All these electrons aren't just going to come to this end. They're actually going to flow right on down into the giant electron sink of the earth ground. And if, while this rod is still close, you cut that wire and disconnect it from ground, now you have a positively charged rod and a negatively charged rod. That is charged by induction. You'll notice that it relied on the fact that both of these rods are conductors, that the electrons in the atomic structure are free to move from atom to atom or molecule to molecule. Other substances like rubber, amber, glass, the electrons in these atoms and molecules are very tightly bound to their host atoms, and they're not free to move readily from one to one, from atom to atom. Those are what we call insulators or dielectrics. And of course, you're all familiar with the middle class of semiconductor. You typically, germanium and silicon. Silicon? Yeah, silicon. Go back now to this water molecule. This is why it becomes what we call a polar molecule. And at some point we are going to talk about dipoles, not necessarily today. But you can see how the electric charge can redistribute inside that molecule so that up close it does look like it's negative on one side and positive on the other side, and it becomes a bipolar. It becomes a polar molecule. What effect would that have, with that phenomenon, and in particular that molecule, water molecule? What effect does it have on static electricity? When does your carpet make your doorknob most hazardous? When it's dry, when the air is dry, when there's no moisture. If you have low humidity, you touch you can get shocked much more easily. Why is that? Because if there's high humidity, even though you might build up an electric charge, there's water molecules in the air that come in contact with your skin. They're going to absorb those electrons and pull them and draw them away from you, and they will actually become ions. So it becomes H2O negative, a water ion, ionized water. And they will draw that extra charge off of your body or off of the whatever mechanism you're trying to do the experiment with. So hopefully when we do this, it'll be a dry day. When we do the lab for all of this stuff, which I think is next week, hopefully it'll be dry. It's winter, pretty good chance it'll be dry enough we can do the experiment. This is why it is so difficult. This is why the physics labs dealing with static electricity can be so difficult, because if you have a high humidity day, you can fight with all that apparatus all day long and it just ain't going to work. So if we do encounter that kind of problem, then you might have to just sort of take my word for it that if it were dry, this is what would happen. Let's see. Electric charge. Induced charge. Coulomb's law. Everybody here has probably already dealt with Coulomb's law. Here's a good place. There's some empty board space. Has anyone not dealt with Coulomb's law yet? Okay, let me ask the other way. How many of you have worked with Coulomb's law? No, not every. Okay, well. Okay, well, let's look at it a little more closely. That is one form of Coulomb's law. What it says is that the force that one charge exerts on a second charge is equal to a proportionality constant, is equal to the product of the charges with a proportionality constant divided by the radius squared. What does that look familiar to? What does that look similar to? Force due to gravity equal to a constant times mass 1 times mass 2 divided by r squared, where the constant in that case is Newton's universal gravitational constant. That's how you calculate how much force the Earth is going to exert on your mass, or vice versa. Looks amazingly like Coulomb's law. So, now, the question then, well, before we get to the question, let's talk about the fact that it's r squared and not r. This makes it, just like gravity, an inverse square law. That means if you double the distance, what happens to the force? If cut in fourth. If you double the distance, the force goes down by 2 squared, or 4. So if you increase the distance by a factor of 3, you decrease the force by a factor of 9. I do want to talk about this constant and specifically how it relates to one called epsilon naught. If I can get the stupid pages to separate. Now, K, if we're going to talk, and if we're to 4 significant digits, is 8.9998 or 999? 998? Yeah. 8.998 times 10 to the 9th. What are the units? Well, we know force is newtons. So this is going to be newtons times meter squared and divided by charge squared, Coulomb squared. So the forces, the units of K are newtons meter squared per Coulomb squared. Now this is an issue. Well, maybe it's just an issue for me. Now, the people in charge of such things over in Europe have decided that the amp is the fundamental unit, and that coulombs are defined as amps and seconds and other. I learned that the coulomb is the fundamental unit. It's the charge, and it's specifically, what is it, 1.9 times 10 to the minus 19. It's order 10 to the minus 19 coulombs per unit per electron. The charge on a single electron is something in the order of 10 to the minus 19 coulombs. And amps were defined as coulombs of charge per second. Okay, well, they've changed that now. So it's amps are the fundamental unit, and coulombs are defined in terms of amps and seconds. Here it is. The charge E of one electron is 1.6. I've done forgot. Walked away and 1.6022 times 10 to the minus 19 coulombs. That's the charge of a single electron. That's the number that I will look for. And I used to know it by heart. 1.68 coulombs per second. Is that an amp? I used to know that number by heart. Doesn't matter. Don't worry about it. It's not going to, I doubt that you're going to run into it in your book. There is a, yeah, it's right here. There's another constant called epsilon naught. And that is, it is the permittivity of free space. Let's see if they've got it written down in here somewhere. I'm sorry, say again? Yeah, that's exactly it. It is equal to 1 over 4 pi times k, which makes it equal to 8.85 times 10 to the minus 12 coulombs per Newton, coulomb squared per Newton meter squared. And that means that you can rewrite Coulomb's law in another form, where instead of multiplying by k, you'd write it as 1 over 4 pi epsilon sub naught Q1 Q2 over R squared. Now, I suggest that you make note of both forms of Coulomb's law, because at this point in this section, in this chapter, I don't think it's going to be an issue. But at some point, we're going to get into topics later on in this semester where epsilon sub naught is going to be a much more convenient constant to use, especially when we start reconciling electricity and magnetism into a single unified theory. We got just a few more minutes. I'll give you an example here on how to use Coulomb's law to calculate the force that an electron exerts on a proton, or vice versa. One I want to point out to you specifically is the problem, the conceptual problem, example 16.2. They say you have Q1, and I don't know, it's 10 times Q2. So one charge is much greater than the other charge. The question is, how much force does Q1 exert on Q2? And how much force does Q2 exert on Q1? And what's the difference? Well, without looking down at your books, just right off the top of your head, what's the first, just guess. What do you think the difference would be? The difference, well, Q1, the force that Q1 exerts on Q2 is equal to K times Q1 times Q2 divided by r squared. Now what's the force exerted by Q2 on Q1? Force of Q2 exerted on Q1 is equal to K times Q2 times Q1 divided by r squared. So the difference is 0. And Newton's laws that if the force that is exerted, every force has an equal and opposite reaction. If mass A is exerting a force on mass B, then mass B is exerting the same force on mass A. The force in this case is the same either way. Whatever force Q1 exerts on Q2, that's the same force Q2 exerts on Q1. Now, are there any questions? For example, does anyone want to know what your homework assignment is? Has everyone signed the roll sheet? Where is it? Who has it? Okay. All right. Homework assignment. And turn this off.